So I am recording now. Yay. All right, so let's do from the 2019 exam. Let's take a look at number 3. And it says a projectile launcher consists of a spring with an attached plate, as shown in the figure. When the spring is compressed, let me zoom in here a little bit. I can hardly read it. It's the old age problem. Let's just do part A. A projectile launcher consists of a spring with an attached plate, as shown. When the spring is compressed, the plate can be held in place by a pin at any one of 3 positions, A, B, or C. For example, figure 2 shows the steel sphere placed against the plate at position C. The sphere is launched upon release of the pin. Okay, so there's the uncompressed. Yeah, okay. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compressed distances. Okay, so the student plans to test the hypothesis by launching the sphere using the launcher. State a basic physics principle or law the student could use in designing an experiment to test the hypothesis. So, what basic physical principle or law? So what they're saying is this, that you know, here's the spring, and it's you know what, I'm gonna take this off. Oof. So here's the spring in relaxed position. So we're going to move it here, and then here, and then here, and we're going to fire this projectile. Oof, it's going to go off out that way. And we want, and the idea is that the spring constant is a constant. The student hypothesized that the spring constant of the spring inside the chamber has the same value for different compression distances. So that means that K that the spring constant K is the same no matter what. So what do you guys think? What physical principle could we use to determine whether or not the spring constant is the same?
A law of conservation of mechanical energy?
Yeah, that's what I would use right away. Now, and I think that you can't really use Newton's second law with the kinematic equations because the force isn't constant and therefore the acceleration isn't constant. So yeah, I would use, state a basic physical to test the hypothesis. I would say, just as you said, conservation of mechanical energy. Okay, so that's cool. Now, using the principle or law stated in AI, determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with the equipment usually found in a school physics school laboratory. Okay, so here's how I would do it. I would want to measure the speed. So here's what we can do. We can say that that the energy of the system is going to be conserved, right? E initial equals E final. Well, E initial is going to be 1/2 the spring constant K, and then it's whatever the amplitude is squared. I'll just call it X squared equals 1/2 mv squared. So if we can solve this for K, so notice that the 1/2 goes away. And so we can say K will be equal to mv squared over x squared. Now x is either going to be c, b, or a. I mean, these are, c is a distance, b is a distance, a is a distance from the equilibrium position of that spring. So this gives us an expression. But the thing is that we're going to need to measure, the velocity. Okay. And so now you can also measure the mass. Use, let's see, what does it tell us to do? Determine an expression. Yeah, so it just wants the expression here. So this is my answer. We can figure the mass out with a balance. We can measure the velocity with a what's called a photo gate or a motion detector, or you can shoot it off the end of the table and figure out how far from the end of the table it goes. That's probably what I would have you guys do, because I don't have photo gates and motion detector, or what are they called? Yeah, motion detectors and so on. So
would we be able to put that as equipment that could be usually found in a school physics laboratory?
yes.
Would they accept that?
Yes.
Okay.
So in fact, I can maybe as part of part B, I'll explain how a photo gate works, and you can use that as something that you would put.
On part 2 for that, we have to explain what the things we would use to obtain the measurements, or do we not have to? Because it just asks for the expression.
Yeah, I think it's just asking for the expression. And so I think what I did, what I have, right here, I think that's enough. I think that's what they're looking for. We can look over the solution guide here in a second when we're done with this problem. Okay, so everybody good with part A? Any questions before we move on? Part A. And I'm glad to hear your voices, you guys. I like that. All right, let's do part B. It says, design an experimental procedure to test the hypothesis in which the student uses the launcher to launch the sphere. Assume equipment found in school physics laboratory is available. In the table below, list the quantities and associated symbols that would be measured in your experiment. Also list the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them to the space below the table. So based on, well, let me rewrite. What was the equation I wrote down? I said K equals mv squared over x. Is that right? X squared.
Yeah.
So we need to measure mass, m. And how are you going to measure it? Use a balance. Or you could say a spring constant, and then you have to divide by 9.8. And I would put little explanations like that. We have to measure velocity. And we could use v. What equipment can we use? We can use a photo gate, or you can use a motion detector, although photo gate would be better. Now let me explain what a photo gate is. A photo gate, and it's kind of hard to draw. Let me, so a photo gate. It's a little thing that it looks like a horseshoe. Let's see if I can draw this. Oh, I'm doing a terrible job of drawing this thing. And it's connected by a wire. And what happens is that it has a little laser that zips across here and a detector over there. And so what happens if you were to shoot the ball through the laser, it'll block the light, and it will tell you how much time the light was blocked. And then you have to measure the diameter of the ball. Ooh, that would be good. And to get the, and then you plug that in and you get the speed of the ball. Now, so probably if you use a photo gate to measure velocity, let's look at that a little bit more. Let's come back to that. We're also going to need to measure x, and that's position, right? And we're going to use x, and we're going to use a meter stick or a metric ruler or whatever. So if you can measure velocity, position, and mass with this equipment. Now a motion detector, if let me explain how that works. If you have an object that's moving, you know, like, and I don't need to do that. I don't need to have the, let me redraw that. So here's the ball coming out, and you have a motion detector, and what it does, it's just this big blocky looking thing that's connected to a computer, and it sends out a sound pulses, and then those sound pulses get reflected back, and it measures the time it takes, and from that it can get how far away the object is. So it gives you the range of the object, how far away it is. But then then pretty soon the next pulse it gets back quicker because the object is closer, and so it has an algorithm in it that can determine the velocity and the acceleration of it. So that's one way to do this. Now, another way of doing this, if you don't have a photo gate and you don't have a motion detector, which I don't have, then what we can do is, let me clear this. Oh, I didn't mean to clear everything. Oh well. This is so annoying. Oh, wait, I can back up. Undo. Hey, there we go. Let me erase the photo gate just to make room. You don't have to erase it. What if we put this thing on a table? So let me draw a table. This is how I would have you guys do it with the primitive lab equipment I have. So here we have a table. And we have H. And here's your shooter. And it shoots the marble horizontally, and it goes down like this. Well, you can figure out the speed. If you know height, if you know the height, you can figure out how much time it took. And then you can measure the distance, and we can call that d. And from that, we can figure out what v is, right? Because v is a velocity in the x direction, and that's going to be equal to d over t. Not d. Sorry, hold on. It should be h. No. I'm right. I was right. The distance, delta x over delta t, right? That's velocity in the x direction, so that's going to be d over t. But how are you going to measure time? Well, I suppose you could put that in there and measure time with a stopwatch or whatever. But what I would do is is measure the height, because we know that delta y equals v naught yt plus 1/2 at squared. Now, the initial velocity in the y direction is 0. So I can solve for time. And we've done this problem many times, right? 2 times delta y over a, take the square root. And so now you could plug that in here to get the velocity. So in other words, we could write another expression. K is equal to m times v squared. Well, what is v squared is going to be v squared over 2 delta y over, it's really g, let's just make it g, the acceleration of gravity, over x squared. So then I would have to put distance, we'll call it d, measured with a meter stick. And then we would have h, which is the height. And it would be good if you drew a diagram to identify where these variables are, the way I've done h. And we would use a meter stick.
But if you said photo gate or motion detector, you wouldn't have to do all of that, right?
I don't think so. I don't think so.
Okay.
You know, because although with the photo gate, if you use the photo gate, you're probably going to have to measure the diameter of the ball and then take the time the photo gate gives you and divide that into the diameter of the ball to give you the speed of the ball when it came out of the shooter. Because what it does, what a photo gate does is it measures how much time that light has been blocked. And so if you know how much time it was blocking the light and you know the diameter, you know, assuming that the light goes right across the diameter of the ball, then you can get the, you can calculate the speed. But one of the things you can do, especially if you're doing this on paper, you know, you can draw diagrams and then, you know, put your variables on there and then fill that chart out. And I'm sure that they'll be impressed with that if you do that properly. So anyway, I think I've overdone this. There's 3 different ways of doing this. This way is, this method right here is the most complicated, right? Because you have to use kinematics, you know, projectile motion and all that kind of stuff. But you only need a meter stick. You need a meter stick and a balance to do the lab. And this actually would be a pretty good lab. So now I assume that part B, that over here, it says describe the overall procedure to be used to test the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances, referring to the table. Provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use the symbols defined in the table and or include a simple diagram of the setup. Okay, so I kind of drew that diagram already for you. And what you need to do is write out the steps. You know, step 1, you know, measure the height of the table. Step 2, measure the mass of the ball. 3, place the shooter at level, I don't know, what was the first one? A? C. It doesn't really matter which one you start with. Oops. And just explain what you're doing and what you're measuring and how you're measuring it. Now, one of the things, take 3 trials at each shooting position. And then you can, you can take an average. In other words, one of the things they really want you to do is in your procedure, list, make sure that you say, hey, I'm going to do this like 3 times for each thing. And if they're, if they're all close, unless there was a big outlier or mistake, because that should average out your, that should reduce your level of uncertainty. Or at least they'll give you an idea of how much uncertainty you have there. So now we've done this in class. I had you guys write procedures before. So it's pretty much the same thing, the sketch and the steps. That's one reason I have you do it, is to draw a sketch and then write out steps on exactly how you're going to conduct the experiment. And we'll take a look at what and how they're grading this here in just a second. Now let's see. It says, describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. Well, I would say, what do we say? K equals mv squared over, was it x squared? Is that right? I would, I mean, you could solve for K where x equals A and x equals B and x equals C, and make a table and compare what x or what K is. Or you could graph K as a function of x, and then you could put like A, B, and C, whatever those distances are, and and then plot what K is. Now it should be a horizontal line, right? If K is the same no matter what x is, then you could that's one way you could do that. And then D, another student uses the launcher to consecutively launch several spheres that have the same diameter but different masses, one after the other. Each sphere is launched from point A. Consider each sphere's launch speed, which is the speed which is the speed of the sphere at the instant it loses contact with the plate. On the axis below, sketch a graph of launch speed as a function of sphere mass. Well, really what we're going to do is we're going to take this expression and solve it in terms of V. So V is going to be K x squared over m. And we're going to take this, we're going to take the square root, right? Now, what's true about x? X is equal to a. Square root of k and then a squared over m. Now, one thing to notice is that the spring constant and the displacement of the spring is now held constant. So that's not varying. So you can say that V should be a function, well, we're going to have the square root of k a squared, or you could put square root of k times a, it doesn't really matter, times 1 over the square root of the mass. So as the mass gets bigger, the velocity gets slower. And so as the mass gets bigger, the velocity gets slower. Now, what would this function look like? Well, let's just, let me put in some numbers here. I can't really remember. What does a 1 over square root of x look like? Or what? Y equals 1 over the square root of x. Because that's what the shape of this is going to look like. Well, let's see. When m, let's say m is equal to 0. Well, then that means that this will go to infinity. So it's going to come, it's going to blow up. It's going to have a shape like that. And then let's say m is equal to 4. So the square, so it'll be 1/4. Wait a minute. So the speed is going to decrease, yeah. So I think it's going to look something like this. It's going to, the rate, it's going to, I think that's a 1 over square root function right there. I think that's right. Something like that. So B is proportional to 1 over the square root of the mass. Okay, let's take a look at solutions, because I am a little bit. Oh yeah, it does. Well, let's see how we did here. For an equation that is consistent with the real, let's see. Well, this is pretty vague. Okay, I'm pretty sure what I did was right though. For each quantity, you get a point describing the, so here's an example, a massive sphere, spring compression, distance, use a ruler. Oh, there we go, launch a sphere, motion sensor, I called it motion detector, motion sensor. Oh, here we go. Here's the example, and I apologize, I should have read this ahead of time. I've just been kind of flaky and busy. But mass of the sphere, spring compression distance, horizontal displacement of sphere. Remember that's what we did. Of course, I called that D, so that's all right. Vertical displacement of sphere, delta Y. So this is kind of the experiment I would have had you do in my class without a motion detector and all that. But it really helps if you draw like a little maximum vertical displacement of sphere. What the heck is that? Oh, I see what they're doing. Oh, that's clever. I didn't thought about that. If you take the, this would be a good way to do it. If you take the shooter thing with the spring in it, and you shoot it up, straight up, and you measure, somehow measure the height. We'll call that, what do they call it? Maximum vertical displacement of sphere, delta Y. Now, delta Y should go all the way from like, here's A, right? So it should go from A to the maximum height above the gun. And so what you have here, when the gun is right here, you have 1/2 K A squared. And then when you shoot it all the way up here, that's going to be gravitational potential energy. which is going to be mgh, and h is going to be that delta y plus this distance here, right? This distance that you compress it. Well, hold on a second. If I'm defining delta y to be the height above the gun, no, we can do this. We can define delta y just to be from where the ball or pellet or whatever it is starting from, so that'll keep it simple. And so now we have k, is equal to 2mg delta y over over x squared, just based on the way we defined it. So that would be another way of doing it. You'd have to have like maybe a video or something like that so that you can look at the video and measure the height where it stops. So that's another way of doing the problem. So there's different ways of doing this. So if you're going to have to be flexible and nimble and just say, okay, if I was going to figure out what that is, what's different ways of doing it. I'm going to let you read through all this. These are the different examples for analyzing it. And there's my graph. Yeah, my graph was fairly accurate. Another student, for a curve where a launch speed always decreases with increasing sphere mass, you get a point. For a curve that is entirely concave up and has the launch speed always decreasing with increasing sphere mass. Yeah, there you go. So, but I went ahead and I went and said, hey, the speed is going to be proportional to 1 over the square root of the mass. And because that's what this graph here looks like. And I was getting a little confused, but what I did to unconfuse myself, I said, well, what if the mass is 0, then we have an infinite launch speed, which is impossible, but so that means you have an asymptote right over here. And then of course, as the mass goes to infinity, the velocity is going to go to infinity. So it's going to have to go down like that. Of course, the mass will never get to infinity, but the speed, as the ball gets heavier and heavier, the speed it launches gets less and less. So you can get the general shape of the graph, even just by using common sense. If the pellet is heavier, it's going to be harder to move for that spring, so it's going to have less speed. So there's that. Any questions on this problem? Oops. Okay. So give me a thumbs up if you got it. So making sense? I want to see that you're awake. I don't want you playing this. What is that? That Switch? That new game? The Switch thingy? I don't know.
Animal Horizon.
Yeah. I think that's why people don't show me the videos. They're really, I don't know, playing video. I'm joking. Okay. Let's go to the next exam. Screen. Now, I took way more time than you get to do that problem, but I was explaining as I went. And now this is the first year. This is the only test I think we've done all the free response tests. I think we've done all the tests. So, so I feel pretty good about that. But there are lots of resources online, you guys. So make sure you take advantage of them. If you're taking what I'm doing right now is kind of the minimum that I expect you to be doing to get ready for the AP test. I do have students that aren't going to take it, so that's fine. They just need to do this. But if you are going to take that AP test, I would recommend that. And also, if you contact me through my cell phone or whatever, and you want a special Zoom meeting in the afternoons or just a half an hour, you have some questions for me, text me and say, hey, Lake, can we have a Zoom meeting? And I'm a free, you know, and if I can, I will do it. I just haven't had anybody do that. Okay, so let's do one more problem. Oh, geez. I just got a message from Tesla. All right, let's do this one. And this one's a shorter one, right? Says two blocks are connected by a string of negligible mass that passes over massless pulleys that turn with negligible friction, as shown in the figure. The mass M2 of block 2 is greater than the mass of M1. The blocks are released from rest. Okay. So the dots below represent the two blocks. Draw free body diagrams showing and labeling the forces, not components, exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. Okay, so we have this string here, right? We've got tension in that string, and the tension is the same everywhere in that string. Now, here's the trick to this. M1 is going to have a tension force pulling up on it, and I'll just draw it like that. And we'll call that F sub T for tension force. Now, block 2 has the same tension force, right? Because those are massless pulleys, and all they do is change the direction of the tension force in the string. They don't change what that tension force is. So you got to draw these, but they have to be the same length. Now, for M1, we're going to have weight. So maybe I'll take it down like this. So this is, I'll just call this M1G. Or you can say this is the force of gravity on 1 equals M1G. Now, the force of the gravity on block 2, I'm going to draw it like that. And notice something here. This on object 1, mass 1, it's going to accelerate up, right? If you were to release that, this block has more weight, so it's going to pull down more than this pulls down. So you have a net force that's going to accelerate this. So block 1 is going to accelerate up, and block 2 is going to accelerate with the same magnitude of acceleration, but it's going to accelerate down. And so that means if block 2 is going to accelerate down, this M2G, this force right here, has to be greater than this force. But on the other hand, this force here, the tension force acting on block 1, has to be greater than the weight of block 1. So that's what I've shown here by the relative magnitudes of those forces. Okay, does that make sense to everybody?
What are the conditions necessary for the tension force to be equal for the two masses in any problem?
If you have a pulley system, if it tells you that the pulley is massless and frictionless and all that, it's not affecting the tension in the string. But if you had a problem like this, and you let me know if you can't see this, because I'm drawing it off to the side, but let's say you had a fixed pulley, like here's the ceiling, and we have a string that holds this pulley in place. And, you know, here we have, you know, M1, and maybe over here we've got a bigger one, M2. And so this thing is going to accelerate around like that, right? If you release them, M2's got more mass, so it has more weight. Now, but if this pulley right here is massless, that means it takes no force to make it spin. That means it's not affecting anything. The only thing it does is change the direction of the tension force in the string. It changes the direction of the string. That's the only thing it does. But if it does have mass and the string doesn't slip, then the tension force is going to be different, because now, if I drew a free body diagram of the pulley, this pulley is being angularly accelerated like this, right? That means there has to be a net torque on it. So if I have, this tension force, I'll call this FT1, and here I'm having FT2. Now, normally FT1 and FT2 would be equal, but if you need some, if the pulley has to be, if you need a net torque to make it spin because it has mass and rotational inertia and all that kind of stuff, then what you have to do is relate these two, because the net torque equals I alpha, where I is the rotational inertia of the disc and alpha is the angular acceleration of the pulley. I'm not disc, the pulley. And you have to say, oh, okay, well, we got R times FT2. It's trying to make it spin this way, and I'll make that way the positive direction, minus R times FT1. Because that's the torque, right? You have R times F gives you torque. So that's when the tension forces in the string will be different going around a pulley if the pulley has mass and if you need a net torque to turn that pulley. Because if these two forces were equal, if FT1 and FT2, if they were equal in magnitude but opposite in direction, then these two torques would be equal and you'd have zero net torque. You wouldn't have any angular acceleration of the pulley. Or you could say, maybe the pulley's spinning, but its rotational inertia is essentially zero. If it's massless, it has zero rotational inertia. And that would allow the tension forces to be equal. Does that answer your question adequately, Abby?
Yeah, and I just have a follow-up question.
Sure.
So whenever the pulley, we're assuming, or when they tell us that the pulley is massless, regardless if the two masses are in motion or not, the tension force is the same?
Yes,
Okay.
exactly. Exactly.
Okay, thank you.
Okay, so this is my answer for part A. Let's check part A. Oh, wait, no, I can't. I have to. I know what I'll do. Still scribble all over my screen, but I don't want to take the scribble off just yet. Oh, it doesn't have the solution guide. Huh. I thought I had the solution guide on there. Let me find it. Where is the solutions? Maybe I don't have it. Oh, it's not in my collection. Well, we'll find it here. You know what? I'm just going to get rid of the screen, and I'm going to pause the recording because this is going to. Okay, so here's the solution guide. And they, you know, the magnitudes are a little different, but the quality is the same. So you notice how these two tension forces are equal, but this one is smaller than that, and this one is bigger than that. And that's what they're looking for. And you can see how the points are spread out here. For drawing two vectors starting on the dots that point upward, have the same length and labeled as the tension force. Now they labeled it, you know, they label it with the word tension. If you put F sub T, they're going to know what you're talking about. So don't freak out about stuff like that. They're very understanding that, you know, they're about things like that. Now, if you don't label them, then yeah, you're going to lose a couple points or lose a half a point. I don't know. For drawing two vectors starting on the dots that point downward, and you know, yeah, so we did good. All right, let's do. Oops, wrong test. So let's go down here. Derive the magnitude of the acceleration of block 2. Express your answers in terms of M1, M2, and G. So let's do that. Here we have block 2. And I'm going to do this the hard way first, which is I think what they're thinking. So here I have M2 times G, and here I have the tension force. And so if I sum the forces in the y direction equals ma in the y direction, let's make down positive because I know it's accelerating down. So I'm going to say, okay, M2 times G minus the tension force equals M2 times A. Hey, okay, but here's a problem. This is all I want to have in there. And look at F sub T. No, we don't want it to be in that equation. So what do we have to do? Well, we're going to go look at the other block, which I'm going to do off to the left here. Here's block number 1. So you've got M1G. And then I've got FT right here. Oops, FT. And we know it's going to accelerate up, so I'll make that the positive direction. And if I sum the forces in the y direction, it's going to be equal to M1 times A. In the y direction, I've got FT minus M1G equals M1A. So what this lets me do is solve for FT. So FT equals M1 times A plus M1 times G, or we can make it a little simpler. FT equals M1 times A plus G. No, actually, we don't want to do that. We want to do that because we're going to solve for A. So what I do is I take this and I substitute it in here for FT. So I get M2 times G minus FT. So minus this. So minus M1A minus M1G equals M2A. So now what I got to do is I got to isolate the variable. I got to solve for A now. So I'm going to add M1A to the other side. So that gets rid of it. Now I'm going to factor out the A and divide. So A is going to be equal to M2 minus M1 times G over M1 plus M2. And there we go. So you have to draw a free body diagram of both of them, come up with force equations for both. You're going to have 2 equations and 2 unknowns. And it's a big pain in the butt. That's a lot of work. Yes? That is a lot of work. So I'm going to show you, and I've shown you this trick before. There's another way of doing this, and that is combining it all into one free body diagram. Then you don't have to worry about the tension force. Watch this. This is Beautiful. So let's, I'm going to redraw it. So here's M1. Here's the pulley. Here's N2 times G, like this. Now what I'm going to do is I'm going to straighten it out. And we've done this before. So here we've got M2G. This is the weight. But now in my imagination, I make it horizontal. And then here's M1 times G. Now I'm going to make this my free body diagram. Woohoo! And if I sum the forces in the x direction equals ma in the x, and this is, I'm going to make this the positive direction since it's going to accelerate to the right in my little pretend drawing. So let's do that. Here we've got m2 times g minus m1 times g equals ma. But what is this? That is the mass of the free body, the whole thing. I have combined these two to be one object. So the mass of that object is m1 plus m2 times a. And so now I can solve for a. A is equal to, well, let's just go m2 minus m1 times g divided by m1 plus m2. And that's the same answer I got before, isn't it? But this is a lot less work. Why? Because look, by combining them, I'm like doing that two equations and two unknowns, but I combine them in, because look, where's the tension force? Oh, the tension force acts on M1 right there. But the tension force, you have an equal and opposite tension force acting on M2. And since they are internal to your free body diagram, they just cancel each other out. They are not part of your force equation for that free body. Isn't that special? Does this make sense to you guys? All right, we're going a little over. Let's see what else is. Let's see what's left. I really want to get done with this problem anyway. Oh. Oh dear, now we've got a block of mass M3 is added to the system as shown below. There is no friction between block 3 and the table. Okay, indicate whether the magnitude of the acceleration of block 2 is larger, smaller, or the same as in the original 2-block system. It is smaller. Because look, let's redraw that free body diagram I just did. Now here I've got the weight m2 times g, and here I've got opposing it is m1 times g, the weight of 1. Now of course m3, right? It's got it's got its own weight and its own normal force, but they just cancel each other out. They're not accelerating the system at all. They're not trying to change the motion of anything. And especially because it's frictionless. Now, if there was friction in here, you would have to add a friction force to your free body diagram, but there's no friction in this problem. So now when you do this, okay, sum of the forces in the x direction, you have m2 times g minus m1 times g equals ma. But now look, this is m1. Look at what's in my free body. m1 plus m2 plus m3. So in other words, more mass is being accelerated by the same net force. The net force is the difference between these two weights. More mass, same net force means less acceleration. And so you might want to explain that in words. Greater mass means less acceleration for same net force, something like that. Okay, let's see if how this matches up with the solution. Oh, let me clear my screen. And it says part B. Oh, here we go. See, there we go. There's the answer to that. And then this one, let's see. Oh, these are just alternate solutions. I wonder if this is, yeah, the system of two blocks must use it. So the acceleration of the system is the acceleration of block 2. Right, so here they're kind of doing my shortcut method, figuring out what the acceleration of the entire system is. So I did show you how to do that. Now, the acceleration of the new system, and thus the block 2 is smaller. Okay. For indicating the mass of the system is larger, you get a point. For a clear indication the tension on block 2 is greater. Did they ask for that? Well, I didn't say that explicitly. Maybe I would have lost that point. It's interesting. Although I think I deserve full credit because I said more mass, same difference in force, because I was combining it. If you were just drawing a free body diagram of M2, then, you know, here's M2 times G. And then, well, tension force would be shorter, but here's your tension force. Then this is going to be greater because you've got more mass that has to be pulled by that string on the other side. So anyway, okay. So where are we at? Let's go. We're going to have a Zoom meeting tomorrow. I think we'll do the last 2 problems of the 2015 exam. Remember that your notebooks are now at school that you turned in last time. So they're in a paper bag. So just tell them what period you're in. They'll get the right bag. They'll hand the bag to you, and you have to dig out your own work. And it's a little bit, I don't know. It's the best I can do. And so you can use that. You know, if you have work in there you need to study, you should probably get it right away. Your AP exam, I believe, is on the 14th. And oh, let's go to the updates. Please check out this website right here. This will give you a nice little video explaining how, if you play this video, I don't know if you can hear it, but you know,
laptop, tablet, or phone. If you're typing on a desktop or laptop, you can reduce the size of your browser window.
So that'll so there's information on this and so on. Also, there are lots of people have made videos of different tests and practice tests. There's a practice test online. Go ahead and, you know, do them. And as I said earlier, but I don't think everyone was online yet. If you have a question, send it to me. You can either, probably the best way would be to text me a question or say, hey, like, can we arrange a Zoom meeting and suggest a time? And then I'll send out a thing. Hey, I got a few people that have questions. And so, but I really don't want, you know, to have a formal required Zoom meeting like to do that. We can have, it'll be totally optional. Okay. So, oh, there's a message in chat. Oh, okay, yeah. All right. Any questions before we call it a day? Well, I wonder how my AP6C students did. They're done by now, I think. I'm going to hear some very sad comments, I'm sure. The AP test always makes you feel depressed. But people always do better than they think. Yes, vote for ASB officers. All right, well, that is,
Oh.
Oh.
okay, show me your faces and wave.
All.
Bye.
Thank you, Logan. Hey,
Awesome.
Brendan. Wave goodbye, and then you can end this. Thanks, Robert. Colby, I never see your face. There he is. Okay. Bye, Colby.